Uh, Hello, I'm Sunho Park, and in this talk, I'm going to introduce our work on verifying lock-free traversals in lex memory separation logic. As the title suggests, our main focus is to verify lock-free traversals, and we consider lock-free versions of linked list or skip list algorithms, and these are used to implement set or map data structure, which support operations like insertion, deletion, or membership testing of a key. And additionally, we consider priority queue data structure, whose main operation is removal of the minimal key in the current priority queue. However, proving these data structures is very challenging, even in the ideal memory model, which is called sequential consistency, or SC. The root cause of this problem is that we have to consider concurrent modifications to the list while traversing the list without locking. So as a result, many people are still working on this topic even nowadays. And in the last year, the first formal verification of skip list under SC was first reported. However, to best our knowledge, no work has fully focused on a realistic memory model called relaxed memory consistency, or in short, RMC. So in this work, our main focus is to build the necessary theoretical foundation to verify these algorithms under relaxed memory consistency. And we report the first mechanized verification of them. Our main results comes in two parts, the specification and verification. And let us first begin with the specification part. In sequential consistency, linearizability has been widely used as a correctness condition of concurrent data structures. Its key idea is to linearize the concurrent execution, and on the linearization and on that total order, we understand the behavior as if we are considering a sequential object. This simple idea is widely applicable in SC, but the problem is that it cannot be extended to the more realistic scenario, which is modeled by RMC. To explain this, let us consider that we are using a modern multi-core CPU, and suppose that we are running multiple threads on different cores. In this scenario, suppose that a thread T1 removes the node 2. However, it may be the case where CPU wrote this new blue edge only to its own cache without writing to the main memory. And if it is the case, then even if a thread traverses the list after the T1's operation, it cannot read the new edge and arrive at the node 2. It results in a situation where T2 still finds the key 2 even if it is executed after T1's operation. Obviously, this is a violation of the sequential behavior of the set data structure, so it cannot be explained by the original linearizability. And moreover, this complex behavior also complicates the verification process. To explain this, I briefly explain the actual semantics of the relaxed memory consistency. Under RMC, the global memory state is the history of all written values. For example, if we store a new value to the global variable x, then the new value is simply appended to the history without overriding the previous value of 0. And whenever we read from a global memory, relaxed memory consistency allows us to read an old value recorded in the history. And in this process, we actually cannot read a very old value that violates the causality. For this, each thread under relaxed memory consistency tracks the knowledge of observation, which is the last value it read, wrote, or synchronized by memory barriers. And using this knowledge, relaxed memory consistency this allows reading or writing very old value which are older than the observed value. And with this model in mind, here's the correct view of the linked list under relaxed memory consistency. Because the global memory state is the history of all written values, linked list structure should be viewed as a directed acyclic graph that contains all the stale edges on the memory. Even more, we have to reason about thread-dependent reachability. For example, we need to prove that this purple edge cannot be traversed by some threads who have observed insertion of the very new node V6. These two parts are very unique but inevitable in elect memory consistency, and these become the major challenge in verification. So in our work, we solved the two challenges, and for the specification challenge, we introduced the method of per key linearization, and for verification challenge, we developed a shadow violation to reason about thread-dependent reachability. Let us first talk about the specification. Our per key specification is based on a variant of linearizability for elect memory consistency, and it is called linearizable history specification. I briefly explain its main idea by using our previous example. As we previously discussed, this scenario cannot be explained in the original linearizability under SC because contained operation of the T2 must fail after the remove operation by T1 based on the sequential behavior of the set data structure. And linearizable history specification fixes this problem by additionally allowing that unsynchronized events can be freely reordered even if their execution times do not overlap with each other. So in this example, we can freely reorder the two operations between T1 and T2, and we can consider this new linearization order. And we can easily check that this linearization order now satisfies the sequential behavior of the set data structure. And in fact, this idea is widely applicable to relatively small data structures like stacks or queues. But the problem is that this idea cannot be applied to more concurrent and complex data structures, especially the set or map data structures we consider. The root cause of this problem is that these complex data structures only have very weak guarantee, and which does not allow to consider this kind of total order at all. And here's a simple counterexample for that. Consider a scenario where T1 and T2 insert the two keys, and then they traverse the list again to find the another keys, 3 and 1. In this scenario, what's unique in elect memory is that both traversals can fail to find the keys simultaneously. This is not appear in the sequential consistency, but this is allowed in elect memory consistency. And if it happens, we can easily check that no linearization order satisfies the sequential behavior. So this cannot be explained by the linearizable history specification. And we have to find a solution to explain this scenario. Actually, what we can learn from this example is that operations on different keys are basically independent of each other. So this means that addition of key 1 has nothing to do with traversal for finding key 3, and addition of key 3 has nothing to do with traversal to find the key 1. And based on this observation, our fix to the previous linearizable history specification is that we are now considering multiple per key linearization orders instead of a single linearization order for the data structure. Here, each per key linearization order consists only of the operations on that specific key. And we actually found that this simple idea has very widely applicable to all our case studies, including the very complex one, the priority queue example. Furthermore, this idea retains the strong power in client reasoning, and we checked it by lots of various client examples. This concludes the explanation to our new specification, and now let's focus on the next topic, which is the verification of the thread-dependent reachability. To explain with an example, let's consider the prior example, and additionally suppose that T1 traverses the list after removing the key 2. Intuitively, this traversal to find the key 2 must fail because that key was previously removed by itself. And actually, this is also what is guaranteed by our specification, so we have to consider this kind of causal reasoning in actual verification. On the semantics level, we can verify this property by using the coherence of elect memory consistency. To elaborate, we can prove that T1 cannot traverse to the node 2 because the coherence of the elect memory does not allow reading an old purple edge after writing a new blue edge. At the essence of this reasoning is a causal order between the two edges, where old edges become unreachable by observing new edges. And one of the main contributions of our work is to formalize this kind of causal relation. And for this, we devised a new relation called shadow pi relation. Shadow pi relation is a relation between two edges on the global memory. And E1 shadow pi E2 means E1 is strictly earlier than E2 in a causal order. So in other words, E1 gets unreachable after observing E2. This is the main intuition behind shadow pi relation. And this relation can be easily established during the insertion of or deletion of each data structure operation. And furthermore, this relation is transitive. And this transitivity is used to establish the causal order between two edges far away from each other. For example, suppose that current thread has observed this purple edge. Then by applying the previous proof rules, we can derive that these shadow pi relations. And now by applying the transitivity, we can prove that this thread cannot traverse to all the stale edges. And in general, this transitivity reasoning can be used to derive the set of all stale edges that cannot be observed by, that is unreachable by each thread. And this is the essence of causal reasoning in actual verification. And the actual model of shadow pi relation is based on the coherence of relaxed memory. Formally speaking, E1 shadow pi E2 means for every traversal to E1, it intersects with what we call reference path to E2. And among the intersection points, we can always find an incoherent step. And due to this existence of the incoherent step, it implies that every traversal to E1 is not possible for some threads who have observed E2. This matches with the intuition behind the shadow pi relation. Here, the reference path is defined in a way that observing E2 implies observation of the entire path. So we can use the coherence reasoning in this definition. And in fact, the reference path is defined in a way defined as the path with all its incoming edges to all its internal nodes. Although I'm not going to explain more about this topic, I briefly mentioned that this precise definition of reference path plays a very important role in establishing the transitivity of the shadow pi relation. And finally, I briefly explain how this shadow pi relation is actually used to verify our Perkey specification. I'll explain with a simple example. Consider a scenario where T1 removes the key 2, T2 finds the key 2 by taking the stale path, and T1 does not find the key, and T2 adds a new key. And in this scenario, observe that these highlighted edges can be sorted by the shadow pi order. So in this situation, our main strategy of deriving the linearization order of these 4 events is based on the shadow pi order, as shown in the screen. The main benefit of this strategy is that we can immediately apply the shadow pi relation to show that this linearization order does not violate causality. So it's only left for us to show that this order satisfies the sequential behavior of the data structure, and we found that it can be done without any major difficulties. So to conclude, we present the first formal verification of log-free traversals in relaxed memory separation logic. And while doing so, we devised a new specification called the Perkey linearizable history specification, and we devised a new shadow pi relation to reason about thread-dependent reachability. And in our paper, more details about specification of complex operations or reason behind the particular choice of the reference path can be found. Thank you for listening, and I'm now happy to answer any questions.
I have a question to get started. So, good specifications are two-sided. That means both the person who implements this specification finds it easy to use, as well as clients. So you told us about how to verify data structures, so you're on the implementer side, but did you also try out if a client of this data structure could use it conveniently? So that's part one of the question. And then part two of my question is, would weak memory artifacts still show up in the specification of a client, or would you be able to hide the weak memory stuff and have a very pretty and simple specification of the client?
Okay, thank you for great question. For first question, we have actually done lots of very in-depth evaluation of the client reasoning, and actually there will be a talk about verifying RCU algorithms on the elect memory, and in that project we employed our per-key specification as a small module, as a specification of the internal module of the RCU algorithm, and we used that specification to verify the entire RCU algorithm. And details will be given in the tomorrow's talk, or details can be found in the paper. So for short, we have evaluated the client reasoning, and it is quite I would say it is convenient to conduct client reasoning compared to some other possible specifications that we have ever proposed. And for the second question, can you reply the separate?
Yeah. So the second part is, I'm not very good at weak memory reasoning. So if I read the specification of your client, can you write it without any weak memory artifacts and just a very simple functional correctness?
Okay. Thank you. And for that part, you can actually you can either choose to hide all the elect memory effect, but in that case you cannot get very very specific. The specification loses its power. So a client cannot reason some very trivial programs without that specification. And our specification contains the bare minimum for the for strong client reasoning. And we tried our best to make it very simpler, but retaining its strong power. So that's our main point of the specification. Thank you.
Do we have other questions from the audience? It looks so, yeah.
Hi, Matthew Parkinson, Microsoft. Thanks for the talk. I was wondering if you had anything about how the memory model you're considering here relates to like the memory models in languages or like at the hardware level, kind of, because you had a very abstract view of sort of weak memory here.
Actually our work is based on the C++ relaxed memory model. So we are already considering the language level relaxed memory semantics. And as long as I know, this language level semantics already captures many parts of the all hardware level relaxed memory semantics. And I believe this C or C++ memory model, especially we are using the operation version of RC11 memory model. It has already incorporates all the hardware details, and I think it is already strong enough to consider many kinds of relaxed behaviors occurring in the either language level and hardware level.
Hi, I'm Dongjae Lee from MIT. Thank you for the great talk. I have a question about synchronizations. So if I know correctly, weak memory has some synchronization mechanisms, and I can imagine that it will interact in some interesting ways with your new specifications and also your verification techniques. And I think I have some question about how they do interact.
can you elaborate more on how, the interaction part, interact with the client part?
So weak memory fences would show up in this history of executions, and that will, I guess, have some effect on linearizability spec.
Okay.
And,
I got, linked memory consistency, the RC11 memory model also has the different kinds of synchronization, which includes using some fences or some least equal synchronization by atomic excesses. And our model, our verification method and the specification does not rely on that part, because reasoning of this kind of internal synchronization is actually done by the previous work that formalized the separation logic for the linked memory consistency model. So you can just use the existing proof rules to reason about the synchronization. And these reasoning principles align well with the previous the IRC11 separation logics predicates or proof rules. So I don't see any difficulties when reasoning about the synchronization in various methods. Yep.
Okay, so it's time for lunch. If you have more questions, you can ask him later. And let's thank the speaker again.